thank you all for coming. I want to assure you, if you have never used R before, that it's not as scary as it might seem. I am not an archaeologist, nor am I a statistician. I'm a biogeographer. I've been working with archaeologists for 20 years. We started in 1995 developing a statewide predictive model for Minnesota, which we completed in 98 and have been using for 20 years and clearly needed to be updated. I have been fortunate that I've had good statisticians to work with throughout all of this time. Carla Landrum, who is my co-author on this presentation, is the current statistician on our project, and she is the one who got us using R. So I thought what I'd talk about is why we decided to go to R and what my experiences have been with R, and show you basically what our procedures are, because we can make our scripts available to anyone else who wants to use any of the procedures that they include. So I'll talk about the R components we're using, our modeling procedures, our results, which I'm really pleased with, and my insights. So why did we use R? We used SPlus for our original models back in the 90s because that's what our statistician at the time, Dr. Gary Ellert from the University of Minnesota, was familiar with. And SPlus is a very expensive package. Carla, our new statistician, was more familiar with R, and it's free. Hey, so that was one of our reasons for going with R. This is just our generalized workflow. Basically, we have our archaeological data that we use to sample our environmental variables. We also sample our variables with a grid of points to represent our total environment, our total modeling region. Feed all of that into the R software. We've been taking it out of the GIS data simply as CSV files, feeding it into R, and doing our modeling, and then spitting out more CSV files that then are converted back into GIS rasters. And I'll talk about why we just use that procedure in a minute. We did actually two types of models in R. We did a historic vegetation model. This was part of our data development stage of our process, where we spent actually a lot more time on data development than on modeling, many years, as a matter of fact, cleaning up the archaeological data, doing quality control, and working on our geomorphic data, which had a lot of different areas had been mapped using different classification systems. We had to get it all into something that was consistent, that we could use. The historic vegetation model was an attempt to model historic vegetation at a higher resolution than what we had available. And I'm pointing it out here simply because we have this script that will do this classification model. And if you have some kind of data that you want to classify, we'll have something you can use, but I'm not going to focus on that today. And then our archaeological predictive model, which is to help us determine either where we should avoid having transportation projects because we have a high potential of archaeological sites, or if we can avoid those areas, to help us target where we need to survey. Our R components, we used R Studio with our notebook. All of these things are free and downloadable from the web. And this is what the interface looked like. The advantage of using our notebook is that it can give you an output HTML file, and this saves a lot of time for documenting your procedures and your results. All of your results will go into this HTML file, and you can simply print it out at the end or save it as in a number of formats. So our notebook was a very handy tool in addition to R. I mentioned that we took our data from GIS into R using CSV files. We originally thought we were going to use our ArcGIS Bridge as the interface between R and GIS. And we started trying to work with that and decided that it really was not worth the trouble. Our files first were too big. We model our state, we divide it into ecological regions to begin with for modeling. So we have 20 different regions that we model of varying size. Our pilot region was not one of the larger regions, and R was really struggling. R wasn't struggling. ArcGIS Bridge was struggling. R was struggling partially because we could not run RBridge in 64-bit mode using ArcGIS software. To run in 64-bit, you have to use ArcGIS Pro, and ArcGIS Pro doesn't have spatial analyst. And since we were doing raster modeling, we needed spatial analyst. So we were having to run it in 32-bit, and of course it just wasn't working with our large data sets. So we just decided that there had to be a better way to use large data sets and go between R and ArcGIS, and that ended up just simply being exporting the CSV files. Worked beautifully. Quickly, I'll go through our modeling procedures. They're very standard, basic procedures. And, if you wanted to, start out with a script that's already written and then modify, this would get you a lot of the real basic analyses that you might need to do. The first part of our script is exploratory data analysis. And I'll point out that Carla, the statistician, wrote these scripts in R and wrote a nice little user manual to go with them. And then the rest of us were completely unfamiliar with R. None of us are statisticians. We took these scripts, we ran through them as she wrote them, went, oh, well, wouldn't it be nice to do this? Ask Carla a question or look something up online, fiddle with the script. We got pretty comfortable with actually making the modifications we needed. Once we had the basic language in front of us and knew what it was doing, we could figure out how we could modify it. So it's not a really steep learning curve as far as I'm concerned. And it was particularly easy for our Python programmer. He was familiar enough with some of the programming language in R that he was able to really extend what we were doing where necessary to get the kind of output that we wanted. Not really changing the statistical analysis, but changing the output parameters so that we got the output we like to see. So our exploratory data analysis staff does all of this very standard statistical stuff and makes lovely graphs. We get histograms. We get these beautiful graphs of the distribution of every variable for the site and non-site locations. Just lovely results that are easy to interpret. We then, after the exploratory data analysis, which we use to clean up the data, we run a random forest model. I don't know if you're familiar with random forest. I'm in love with it. When we did modeling in the 90s, we used stepwise multiple logistic regression because that's what was being used for predictive modeling at that time. Random forest is producing much better models, very precise models. And Carla and I disagree to a certain extent about why we're getting these lovely models. I say, oh my God, random forest is great. And Carla says, no, you guys spent so much time cleaning up your data. That's why you're getting better models. But I think it's probably both. But random forest it's a tree classification method, and it runs a lot of trees is basically what it does. That's why it's called a forest. And it provides some lovely graphics that show you how well it's doing. You can also tune the model to optimize the output. This particular graph is showing it's the graph we use for determining how many variables the model should look at each node on each tree. So you can tune your model by adjusting that. This is it's called the mtry. You can also optimize your model by telling it how many trees to run, and you get another graph that helps you make that decision. So we run one model. This is the graph that helps you determine the number of trees. You see that the error rate drops rapidly as you increase the number of trees, and then it levels off. We run one model that's not tuned, use the output from that model to tune the model to decide how many variables at each node and thank you, and how many trees we want to run for the tuned model. For every model, we also get this lovely graph of how each variable performs. I happen to love this output because it helps me decide whether it's worth developing particular data, running particular variables in the first place. So it tells us the increase in the percent increase in the mean square error if we remove a variable. So the variables up at the top, in this case, cost pass distance to the nearest wetland, would change the model greatly if we took that out. Whereas if we took surface roughness, which is at the bottom, we removed that from the model, it wouldn't make much difference. So we get a lot of information about our variables. We get a lot of good information for assessing model performance. We can run our models based on training data and test it with some testing data. We can do random splits of the data right in R. And we can get a very nice output based on the confusion matrix with a number of measures of model accuracy. We get the rock curves, which show us the area under the curve to indicate, again, how accurate our model is. We can determine our maximum accuracy cutoff. Obviously, our models are, the raw model is a range of values between 0 and 1. And for our interpretation of the model, for the practitioners, we want to have high and low probability areas for archaeological sites. And this curve helps determine the maximum accuracy cutoff. And also we get a numeric indication of what's what number within the model is our maximum accuracy cutoff. Export to GIS and classify it using the maximum accuracy cutoff, and you get a map of high and low potential for archaeological sites. We also tested other decision rules for classifying our models. It turns out that the maximum accuracy cutoff, because we have more background points than we have sites, our models are actually better at predicting the background points. In other places, what are not sites. So our maximum accuracy cutoff, usually if we use that, we have high probability areas that capture 80 to 85% of our sites. And we wanted to see what would happen if we tried to capture a higher percentage. And it turns out we can make our models where we make the decision rule that 95% of our sites are in high probability, and they're still very, very precise and very accurate models. We still have a very high rate of true negatives in our models. So we ended up, to be consistent across the state, using our 95% decision rule for classification rather than the maximum accuracy cutoff. We still have very high accuracy, very high rates of true positives, obviously 95% true positives, and in the 90s% of true negatives. So this shows our accuracy of our final models after they're classified. The very straight line across the top is the percent of sites predicted, the specificity. The green line is the percent of non-sites accurately predicted, the sensitivity. Accuracy is in between them because it's based on both. The blue line at the bottom shows the percent area classified as high probability, which is less than 20% everywhere. And it's much better than our earlier models. And then the gain statistic, Fahmy's gain statistic, you can see is the purple line, and that varies because the amount of area classified as high probability varies. This is what our final model looks like. We model both archaeological site distributions and survey distributions because we know surveys have been not random by any means. Archaeologists survey where they think they'll find sites. So we try to give the archaeologists a head up on what areas we think have been undersurveyed. We don't want to say an area is low probability if we don't have a pattern of archaeological survey there. So these are what our final models look like. They're very, very, very precise, particularly when compared to our previous models. And our insights. Categorical variables can cause some problems, particularly if you have rare values. I won't get into that detail, but if you do have categorical variables, we have procedures for dealing with them. We also had a problem with null values. Our soils data, our values are missing in certain areas, urban areas. Their soils don't have any data in them. Mining areas, disturbed areas. So we ended up doing two models, one without soils data, one with soils data, and then we can use the one without soils data to fill in those null areas. Memory requirements were considerable. Worked a lot better with 124 gigabytes of RAM with 64 gigabytes of RAM, which is what I have on my computer. I could not run some of the regions without splitting them up. And conclusion, you've got pluses and minuses. The costs are whatever it takes to convert from whatever methods you were using previously. Obviously, RAM, if you don't have enough, it's not going to work real well. And there is a learning curve, but as I said, it's not as bad as I expected. The one thing that does bug me about R is that the syntax keeps changing. So if I have one version of R on my computer and everything's running great, and then I tell someone on my team, okay, put R on your computer and run this script, he might download a newer version of R, and there may be some part of the script that doesn't run because they changed the syntax between the two versions. That does bug me. But other than that, we've had great luck with it. Benefits, obviously, it's free. The tools are powerful. They're readily available. You get a lot of efficiencies and replicability from the scripting process. Our notebook really is nice for documentation. And you can actually easily go back and forth between R and ArcGIS without using RBridge. It's really quite simple. So if you're interested in our scripts or our procedures, Google MnModel, not up there yet. We're working on documentation right now. We'll be putting all of this up, we hope, by the end of July, because that's when I'm retiring for good. And So keep an eye on it, and we will be able to share all of our scripts and procedures. And we have some scripts actually that we never ran that Carla developed using other procedures that she said she didn't recommend, but it's other modeling procedures besides random forest. So we have a number of things we can share with people. Thank you.